Imagine standing on the surface of Earth, gazing up into the night sky. The stars sparkle far beyond, galaxies so distant they seem unreachable, and yet, what if there was a shortcut? A way to travel across the vastness of space in the blink of an eye, bypassing the endless stretches between distant stars and galaxies. It sounds like science fiction, doesn't it? But the truth is, this idea isn't as far-fetched as it may seem. It's called a wormhole, and it might just be the key to unlocking the mysteries of space travel. So, what exactly is a wormhole? A wormhole, also known as an Einstein-Rosen bridge, is a theoretical passage through space-time that could create a shortcut between two distant points in the universe. Think of it like a tunnel with two ends, each located at different points in space and time. In essence, a wormhole connects to separate areas of space-time, allowing for faster-than-light travel or even travel to entirely different parts of the universe. Let's take an example. Imagine you're standing at one point in the universe, and you want to travel to another point that's billions of light years away. Without a wormhole, you'd need to travel at light speed or faster to reach that destination, which would take an unimaginable amount of time. But if a wormhole existed between you and your destination, you could simply enter the tunnel, bypassing the enormous distances. The trip would be instant. The stars and galaxies you once saw as distant and unreachable would be right at your fingertips. But how does this all work? Let's break it down. Wormholes are rooted in the principles of general relativity, the same theory that predicted the existence of black holes. According to general relativity, space and time are part of a unified structure known as space-time. This means that anything with mass, whether it's a planet, a star, or a black hole, can warp or bend this fabric of space-time. A wormhole is thought to be the result of this warping, where space-time itself is folded in such a way that two distant points are connected by a tunnel-like structure. Now, this isn't just some wild idea. The concept of a wormhole is mathematically possible. The general theory of relativity allows for the existence of such tunnels in the fabric of space-time, although they are highly theoretical. So far, we have no direct evidence that wormholes exist in nature. They might be extremely rare or possibly undetectable with our current technology. But according to the equations, there's nothing stopping their existence. The idea of a wormhole isn't entirely new. In fact, it was first proposed by physicists Albert Einstein and Nathan Rosen in 1935, who came up with the concept of the Einstein-Rosen bridge. They suggested that a black hole could be connected to a white hole, and the space between them could form a wormhole. A black hole, as we know, is a region in space where gravity is so intense that nothing, not even light, can escape. On the other hand, a white hole is a hypothetical object that does the opposite of a black hole. It expels matter and energy instead of pulling them in. But here's the thing, while the equations allow for wormholes to exist, there are significant challenges. The most immediate issue is stability. Wormholes, as predicted by the equations, are incredibly unstable. If we could create a wormhole, it would collapse in a fraction of a second, long before anything could pass through it. The forces at play would be so intense that the tunnel would collapse under its own gravity. So, how could we make wormholes stable enough to use? One possibility involves looking at how light behaves around these theoretical tunnels. Wormholes are believed to create unusual distortions in space-time, and this could cause light to behave in odd ways. Light passing through a wormhole might bend in unexpected patterns, potentially leaving behind clues that astronomers could observe. In fact, some scientists propose that the way gravitational waves behave could also provide hints about the existence of wormholes. Gravitational waves are ripples in space-time caused by massive objects, and some believe that wormholes might generate their own unique gravitational wave signatures. So, why haven't we found any wormholes yet? The answer lies in the very nature of wormholes themselves. While wormholes are mathematically possible, their existence is purely theoretical at this point. We have no observation of a wormhole in nature, nor any confirmation that these theoretical constructs are more than just abstract solutions to Einstein's equations. However, just because we haven't observed wormholes doesn't mean they don't exist. Some scientists believe that wormholes might be difficult to detect, especially if they are small or located in parts of the universe that are hard to observe. So, if wormholes are out there, how might we go about finding them? Now, assuming that wormholes do exist, what would it take to travel through one? That's where things get tricky. Wormholes are thought to be incredibly unstable. The forces inside a wormhole would be so extreme that, unless we could somehow stabilize it, the wormhole would collapse in on itself before anything could travel through it. In fact, just like a tunnel could collapse if the ground above it is too weak, wormholes might only last for fractions of a second. To make wormhole travel possible, we would need to find a way to stabilize the wormhole so that it doesn't collapse. The key to this could lie in something called exotic matter. Exotic matter is a hypothetical form of matter that has negative energy, meaning it would exert a repulsive force rather than an attractive one. If we could harness exotic matter, it might be able to counteract the intense gravitational forces near the entrance of a wormhole and keep it open long enough for something to pass through. However, exotic matter remains purely theoretical and we have yet to observe it in nature. Let's take a moment to think about the scale of the problem here. The idea of keeping a wormhole open for space travel involves overcoming challenges that are far beyond anything we've accomplished. Even if we did find exotic matter, we would need vast quantities of it. After all, space-time itself is incredibly vast, and keeping a tunnel open long enough to make travel possible would require a lot of energy. The kind of energy needed to stabilize a wormhole is currently beyond our technological capabilities. Furthermore, even if we did manage to stabilize a wormhole, there's the issue of the immense gravitational forces near it. The closer you get to a wormhole, the more likely you are to experience what's known as spaghettification. This is a process that happens when a person or object approaches an extreme gravitational gradient, like the one near a black hole or wormhole. The tidal forces would stretch anything near the wormhole's entrance into a long, thin shape, much like spaghetti. So, any spacecraft or human approaching the wormhole would be torn apart unless it was properly shielded. Let's imagine, for a moment, that you're able to survive that initial stretch and pass through a wormhole. Where would you end up? This is where things get even more fascinating. Wormholes are often thought of as connecting different parts of the universe. But there's another possibility: wormholes might connect different dimensions, or even different timelines. If that's the case, traveling through a wormhole could mean entering a completely different universe, one with different physical laws, or even a parallel version of our own universe where history unfolded in a completely different way. One of the most thrilling possibilities surrounding wormholes is their connection to time travel. If wormholes can link to distant points in space, why not to points in time? Some physicists propose that wormholes could be used for time travel, potentially allowing us to visit the past or the future. But just like space travel through wormholes, time travel brings its own set of paradoxes and questions. For instance, imagine you traveled back in time to a point before you were born. Could you change history? Or would you be unable to influence the past because of the so-called grandfather paradox? The grandfather paradox states that if you were to go back in time and prevent your grandparents from meeting, you would never have been born. But if you weren't born, how could you have traveled back in time in the first place? These paradoxes create what's known as the causal loop. It's an issue that arises when you attempt to change an event in the past, which has consequences on the future. Could we ever overcome these paradoxes? Some theorists believe that the nature of time itself might prevent any paradoxes from occurring, perhaps by constraining time travel to a loop where the events still unfold as they were meant to, no matter what. Another fascinating idea is that wormholes might not only allow travel between different points in time or space, they could potentially link different versions of reality. Imagine stepping through a wormhole and entering an entirely new universe, one with entirely different rules of physics. Could we encounter entirely different forms of life? Perhaps even intelligent beings with an entirely different understanding of existence? It's a mind-bending thought, but it remains one of the most exciting possibilities surrounding the study of wormholes. At the end of the day, wormholes remain one of the most exciting and mysterious concepts in theoretical physics. Could they one day become a reality, allowing us to travel vast distances, explore the past or future, or even journey to alternate universes? The possibilities are truly endless. For now, wormholes remain theoretical, but the science behind them opens up endless doors to new realms of exploration. Could wormholes be the key to intergalactic travel, time travel, or even understanding the nature of multiple dimensions? Or are they just another one of those fascinating ideas that we'll never be able to prove or experience? As we continue to push the boundaries of science, we may one day have the answers. But for now, the wormhole remains an enigma, a mystery we can only dream of solving. So, what do you think? Do you believe wormholes could lead us to incredible breakthroughs in space travel, time travel, or even interdimensional exploration? Or are they just a theoretical concept that belongs firmly in the realm of science fiction? Let us know your thoughts in the comments below. And if you enjoyed this deep dive into the possibilities of wormholes, be sure to like and subscribe for more thought-provoking content on the wonders of the universe.